So here we X this out, X this out, X it out. And so do we ever have to consider the concentration of pure water? The concentration of water is 55.5 molar. 55.5 molar. So out of that, how much water reacts in this reaction? Tiny amount of water reacts. Will it change its molarity much? No. I mean, if we consider it pure water, pure water is 55.5 molar, and if I have a liter of water and I drink half of it, did I change the molarity of water much? I didn't change it at all. It's still this 55.5 molar. And so you can do two things. You can include the 55.5 molar here. This is going to be about 55.5 molar. This is, a dilute. This is called a dilute solution. Dilute solution is mostly water. It's 99.99 whatever percent water. So it stays 55.5, 55.5, 55.5. Doesn't really change. There's one problem in the homework where you might put it in. And so instead we say the activity of water is equal to 1. What is activity? Define it for me.
Isn't activity the rate of the reaction?
Not the rate of reaction. The activity of water is 1. Why 1? The definition of activity is the effective concentration. Well, the concentration of water is 55.5 molar, so why are you calling it 1?
Because it doesn't affect the concentration.
Yeah, it doesn't change. It's already incorporated into K, actually, and it's not going to change, so we just call it 1, right? And so this brings up that one homework problem, or 2 homework problems back there. It's just the reason I'm bringing this up is, now is maybe the time to shift the way you study if you aren't recalling the earlier stuff, Maybe now is a good time because then you're going to be way more competitive when you transfer. So anyway, we should have been finished with this a while ago, at least step 1. And when we plug this in, we're going to get x squared over 0.100 minus x. This is equal to 1.8 times 10 to the minus 5. And so did you guys use the quadratic, or how did you solve this?
Quadratic.
You used the quadratic? Did anybody try the simplifying assumption? Did it work? Yeah, the simplifying assumption works here. And so, if the exam is too long, right, and you aren't going to finish the whole thing, the people who use the simplifying assumption will have an edge over you, right? It's not because they're necessarily smarter than you. It's just that they have that edge in speed over you because they'll use the simplifying assumption here and they'll change this to x squared over 0.100. Now, how much time saving is that? A lot. And so all of a sudden they're answering 1 or maybe 2 more questions than you. And so it's a little shift in thinking on the UC. And so this is why maybe the statistic, after I heard that statistic, then I thought, maybe I'm not preparing students well by having these not strictly timed exams. Maybe I should have strictly timed exams, which are too long. So you have to develop that strategy. Maybe I'll change. I don't know.
Next semester.
All right, change next semester. Maybe I won't change.
That'd be good.
But I just worry that, maybe some of my former students are in that 50% dropout. Not preparing them well. Well, anyway, going to this, x is, what did you get? 0.001344.
I got another 3.
Did you get another 3? You did the quadratic?
Yeah.
Yeah, quadratic, you're going to get a better answer, for sure. If you use the quadratic, you've gotten 0.00133.
Yeah.
Fine, which is a better answer. So your answer is better, but will it make a difference?
No.
Yeah, not that much of a difference. A little bit of difference. And so here we're going to have 0.100 minus 0.00134, which gives me 0.09865,
9865.
64, 66,
66.
66 molar. Here we could do a calculation in our head. The calculation we can do in our head is what was the percent hydrolysis? So we started with 100 and we lost 1.3. And so that means it's 1.3% hydrolysis or 1.3% reaction. And so in Chem 1A you learned that weak bases partially hydrolyze, right, or partially ionize. And now in Chem 1B we can come up with a number. If it's 0.100, it's 1.3%. Now is ammonia always 1.3% hydrolyzed? No, because it depends on, let me just talk about this quickly. But the percent hydrolysis depends on the concentration, or can depend on concentration. And so this is typically what we see. If it's strong, it's totally independent, because strong is always going to be 100%, no matter what the concentration is. But this is not a fixed number. It's not always 1.3% reaction or 1.3% hydrolysis, because the percent hydrolysis changes. And so at dilute concentrations, the percent hydrolysis increases. In fact, at very dilute, it gets close to 100% or approaches 100%. But as the concentration increases, the percent hydrolysis goes down. And so we can't always assume it's going to be 1.3% hydrolyzed. It changes depending on what our initial concentration is.
So that's like the general term that as concentration of the base increases, then the percent hydrolysis will decrease. That's the
Decrease
general
for
trend.
weak bases.
For weak bases.
For strong bases, it doesn't matter, because for strong bases, it's always 100%.
Okay.
Okay. And so it's a nonlinear effect, and yeah, this is a nonlinear equation, because linear equations aren't going to have square terms or cube terms or square root terms. So this is nonlinear. All right, for ammonium, we got 0.00134 molar, and for hydroxide, we end up with 0.00134 molar. Now, this is pretty much the end of the line for ammonia and ammonium, but what about hydroxide? Do you expect much additional hydroxide from water collisions? I mean, would those additional hydroxides from water collisions increase the hydroxide significantly or insignificantly? Insignificantly. Why? Okay, the argument you would use here, why? Because the most hydroxide you're going to get from water would be less than 10 to the minus 7. And so would 10 to the minus 7 even impact this? 1, 2, 3, 4, 5, 6, 7. You're adding here. Is that going to make any impact on this number? No, it's too many decimal places out. But you know what? Don't take my word for it. Let's go ahead and do it and then see for ourselves if it adds much or not. And so when we do this for ourselves, well, we got collisions from water colliding with other water molecules, and these are going to generate hydronium and hydroxide. Do I worry about H2O liquid? No. And so I start my ice table over here on the right, because H2O is a liquid. Its activity is 1. Doesn't change anything. Hydronium, I reset this, so I assume that no water molecules have yet collided. And so the hydronium is what? 0. But my hydroxide is not 0. Why? Yeah, because from step 1, I have point, so I'm going to take this down and put it over here, 0.00134 molar here. And so now I let the water molecules collide. It's going to go plus X molar, so at equilibrium I'm going to get X molar and 0.00134 plus X molar. And so let's go ahead and calculate how much additional hydroxide I'm going to get here by looking at Kw. Kw is going to equal the hydronium ion concentration, which is X, times the hydroxide ion concentration, which is 0.00134 plus X. And this should equal 1.0 times 10 to the minus 14 here. The quadratic equation. Would you use the quadratic, or would you try the simplifying assumption here?
You can try simplifying.
Yeah, let's try the simplifying assumption. If we try the simplifying assumption, then this is going to be X times 0.00134 is equal to 1.0 times 10 to the minus 14, which means that X is equal to 1 times 10 to the minus 14 divided by 0.00134.
Use 7.46.
7.46
2 times 10 to the negative
times 10 to the negative 12. 7.46 times 10 to the negative 12. And so that means the hydronium ion concentration, 7.46 times 10 to the negative 12, and then the hydroxide. Well, let's go ahead and add that up here. The hydroxide is going to be 0.00134 plus, okay, so this is the hydroxide I got from step 1, and then hydroxide I get from step 2, I need to have 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros, 746. And then add these two up, so I'm going to get 0.00134 and 1, 2, 3, 4, 5, 6, 6 zeros, and then a 746. Did that contribute much? No. Hey, wait a minute. Did I make a mistake? Because isn't X 1.0 times 10 to the minus 14? This is just Kw, 1.0, this should be 1.0 times 10 to the minus 7, excuse me, and 1.0 times 10 to the minus 7, right? From water. Didn't we see that the other day?
Yeah.
I have a fuzzy recollection that X is 1.0 times 10 to the minus 7 molar. I see this on the test all the time. And I think it's because they have a fuzzy recollection or a strong recollection that X is 1.0 times 10 to the minus 7 for Kw. Right? What did they do wrong? I see this all the time, but they did something wrong here. What did they do wrong? How do you explain it to somebody? Somebody says, I know what X is because this is water colliding with water, so it's 1.0 times 10 to the minus 7. And then you would explain to them what? That's only for pure water. And then they'd say, well, so what? This is just water colliding with water. Should give me 1.0 times 10 to the minus 7 molar. And then you'd say,
Is that because that's the initial at equilibrium? Is the
this was the initial. We did a reset. You know, we did the Le Chatelier's thing and then reset. So you could say Le Chatelier's principle, or you could say what?
They're assuming that the waters are colliding.
The water is always colliding. The water is always colliding at the same rate. Just because we have ammonia in there doesn't change the rate that the waters collide. The waters are always colliding, always producing, but just what's happening? The water is still colliding at the exact same rate as it was before. Nothing's changed.
is it the rate of the forward or the reverse reaction?
It has to do with that. So what did you say? What do you guys say?
So the rate of the
There's no change.
Hmm? What would you say?
The effective change.
We cannot get this population. It's impossible to get 10 to the minus 7. Why? even though that's what happens in pure water, it won't happen here because,
We have an initial hydroxide concentration.
yes, because we have initial hydroxide. And we got a lot of hydroxide here to begin with. Even though this doesn't sound like a lot, it's a lot of hydroxide compared to 10 to the minus 7 molar. And what's going to happen with all this hydroxide? As soon as a little bit of hydronium is formed, it's going to be consumed in the reverse reaction, therefore preventing the hydronium from ever climbing above 10 to the minus 12. 10 to the minus 12 is a tiny amount, right? But that hydronium cannot exceed that because the reverse reaction will take over if it does. And right now it's just balanced. You know, the forward and the reverse are happening at the same rate. And so this, you could use the predator analogy or whatever analogy you want to explain it, why you can't put in 1.0 times 10 to the minus 7. It just isn't going to work. It only works for pure water. All right, are we out of time? Yep. So, the next thing I want you to do or start to think about is this. The next, and we'll do this in class, 1.0 times 10 to the minus 8 molar ammonia. What's the next one we're going to do? I'm going to stop.